to work efficiently. Very good. Okay. Welcome to Lecture 11, CSE 548, the analysis of algorithms. We're passing back the first midterm for efficiency purposes. So we can pass back all the midterms in linear time. We've sorted the exams, and we've sorted the students. Okay? And in linear time, we can now match the students to the exam. So let's go and see how this works. Shirhei Bagley. I may be messing up names. William Barber. Okay? Ingmar Bitter. Roman Botvinnik. Okay, Paul Bailey. Okay, sorry. D. Caesar. Okay, keep going. D. Caesar. Daniel Casero. Okay. Chung Chan. Okay, Igor Chikranian. Okay, Tanram Chewbacca. Okay, sorry about that. Bao Ku Chu. Okay, Jerzy Shizap. Okay, Jules de Leon. Lily Dong, Mikhail Fantanovich, Matthew Fardelloni, Helen Fang, Yugen Gao, okay, Zhonghen Gay, okay, Keith Gordon, okay, Kenneth Gordon, okay, Carmine Guida, okay, Stephen Guz, okay, Brian Horn. Okay. Nae-Min Joang. Okay. Andrew Kim. Bao Sum Wee. There you go. Sorry about that. Chang Kil Lee. Okay. Ji Lee. Okay. Xiaoming Lee. Okay. Zhang Li. Lin Hong. Tai Day Lin. Mo Lo. Sorry. Okay. Charles Lepresti. Zhang Lu. Max Markalovich. Gang Miao. Okay. Andrea Milazzo. Raymond Munzio. Sorry. Cody Nig. David Nig. Ning, I'm sorry. Okay. Paula, okay, Prasanna Paula. Okay, Shikai Q. Okay. Shu Ming Q. Charles Russo. Jacqueline Saunders. Okay, Tantana, there you go. Okay, Oleg, there you go. Paul St. Denis. There you go. Thanda, Thanas, okay, never mind. Sean Torre. Okay. Chi Chao Tseng. Winston Tseng. Okay. Tsu Takwan. Srinai Vanajarjan. Dario Vla. Okay. Fan Wan. Fang Guan, Zhaiming Zhuang, Douglas Warren, Luck Quan Wang, Chin Kwa Wu, Yan Feng Wu, Wei Zhu, Yang Mei Zhu, Dong Yan, Feng Yang. Sorry about that. Xinghu Yi. John Yi. Chao Young. And finally, Lai Ku. Okay, very good. Okay. Again, efficiently distributed. The rest of the exams will be given out after class. Okay. The distribution of scores, tell you what, bring these to the back of the room. Okay, there you go. Okay, the rest of the scores for the exam were roughly binned as follows, just so you get an idea. For the undergrads, the low was a 25 and the high was a 99. Scores in the 90s, you can see sort of how the distribution of scores went. The highest, the single biggest bucket was in the 60s. Okay, while there were several good scores, and there was a Gaussian curve here with a tail. For the grads, the high score was 118. Again, the graduate students had 20 more points on their exam, so there's no surprise that the graduate students did, got higher high. The lowest low was from a graduate student, however. Okay, and again, there were a lot of scores bucketed around, 120, and then it tailed off slowly, okay, down to that. Okay, so as far as what I think is a good score or about the results of the test, this test was, I mean, there were some somewhat tricky questions on it, but I don't think there were any really. I mean, it was obviously the fact that they were essentially perfect scores for both the grads and the undergrads showed that it was possible to do reasonably well on it. I can understand if people got confused about one problem or two problems. So, but the people who I'm most concerned with are the people who did very badly on it. Okay, if you got below, let's say in the 50s or below for an undergrad, okay, especially if you got below 50, okay, or for a grad if you got, let's say, in the 60s or below, okay, I'd like to talk to you about it, see how you're doing, okay, because you may just sort of not be getting what we're trying to do here, and I want to correct if there's problems. I want to correct them now, okay. So if you did very badly on it, I want to talk to you about it. I would say for the undergraduates, I consider very badly to be definitely in the 40s or below, and in the 50s to be pretty bad. Okay, not necessarily, possibly redeemable, but that's the rough way I think about it. For the grads, I'd say anything in the certainly below in the 50s or below, and again in the 60s or below, I'd probably want to talk to you also. Okay, just to see what's going on. Okay. Any questions? I'll go quickly through the test and show what I had meant for this. But that's roughly what the score distribution is. So just quickly, what were the scores that I was looking for? Okay, what was the test problems, or what was the questions? The first questions concerned pairs of functions and comparing their orders of magnitude. The first question is n log n in n square root n. The answer was yes, because you cancel the n's basically, and log n is going to be, within square root n, because log n is going to grow slower than any other power. Okay, that's certainly true. The second problem asks is log n in order n to the minus 1/2. N to the minus 1/2 is 1 over the square root of n. As large n gets larger, this thing gets closer and closer to 1. It never gets, it never gets bigger than 1. Okay? So clearly this thing is increasing. This thing is bounded by 1, or some certainly no more than 1. And so this is certainly not going to be a bound of that. So that's false. For the recurrence relation, asked is Tn, T of n, n over 4 plus order square root n. There were two different ways you could do this. Some people did it by just plugging in the theorem. Some people did it by summing things up. Because if you'll notice that what's happening, if you do back substitution, you get a square root n. Then the next thing you get the square root of n over 4, which is the square root of n over 2. And then in the next round, you get the square root of n over 16, which is the square, when you put the 16, pull it out of the square root, you get a 4. Okay? And so it halves each time. So you've got a geometric series, and this is going to converge. So square root n turns out to be the right bound. Okay.
I only give the big O, right? You can't give a theta bound.
Right. Well, I guess I only wrote a big O bound, so presumably you can't get this could have been a 1. If this was a 1, then it would have been a log bound. Yeah. So okay. So if there's questions about it, okay, think about it. Make sure that you're not the one with the mistake, okay, which is often the case. If that is not the case, go and talk to the person who graded it. Darren is the one that graded it. I graded the 3rd, 4th, and 5th problems. Okay. So presumably there's no mistakes in those. Okay. The second problem, okay, is to consider give a proof or counterexample. Let's zoom in on this a little bit. Give a proof or counterexample to the claim that if you have two functions, it's always true that f sub n is big O of g of n, or g of n is big O of f of n. Okay? And there are a couple, this turns out not to be true. And the way that I think it's easiest to see it's not true is to think about two different functions, okay, which are sort of are quite non-monotonic, okay, meaning they go up and down, up and down, up and down, okay? So suppose we've got some function that's going like this, okay, and another function that presumably in a different color, which I may or may not have, okay, is going something like this. Okay? There is no point beyond which, okay, suddenly it starts being true that one function is always dominating the other. Okay? If you have them, if they're free to move up and down. And there's nothing in a function that prevents it from moving up and down. Okay? Something that if for an even number you set it to be equal to 1, for an odd number you set it to be equal to n cubed. Okay? Is a perfect example of a weird function. Okay? And there's no reason why one is necessarily always dominating the other. Okay? Any questions about that? Or okay? This one was of the first few problems, I think, the tricky one. Okay? The next part of the problem was the Newt-Gingrich problem. You want to take, you have n players, they're ranked by skills. You want to divide them into two teams of equal size, as unevenly ranked as possible. Okay? There was a question during the exam of who was Newt Gingrich. Okay? Which, again, you didn't need to know for this thing. He's just thinking, for purposes that we need, he's someone who wants to do bad things. Okay, that's all you need to know for the purposes of the problem. But what was the idea? If you sort the players, okay, you've got all the players of high skill are going to be the n over 2. The n players of highest skill will be above the median. The n players of lowest skill will be below the median. Okay, so one way you could do it is simply sort the players, okay, and split them into the players above and below the n over second position. If, in fact, you wanted to do this more efficiently, in linear time, you could find the, the median. Okay? One of the homework problems showed a randomized way to do it. In fact, you could have done it in linear time. Okay? And then once you had the median, you could just scan through everybody and say who's above and who's below. Okay? But I didn't ask for linear time. I asked for n log n. Okay? And now, a lot of people said they used quicksort for this. Of course, quicksort could be n squared. Okay, so that might be that's not necessarily going to help Newt do what he wants. Yes.
I was just curious on this problem, like how specific do you want us to be when we're giving the time? Because like mine was off by a factor of 2. Like, does that? Why would you take off points for that? If you my concern would be that you get the asymptotics correct. If you're not happy with what happened, talk to the TA, or write a note on it and explain why. Okay, think about things before you immediately instinctively get hostile. Okay, the TA had a lot of papers to grade. Okay, and there's different interpretations. There's a need to be consistent. Okay, across a lot of people. Okay, and so if the answer is well, that's what he did with every paper, that becomes a more reasonable thing than that he was just out to get you. Okay, any other questions? Okay, very good. The third problem was what I consider to be probably the trickiest problem, or not trickiest, but the hardest problem of the problems that, of the problems on the exam. Okay, the problem asked, how do you modify a red-black tree data structure so that in a red-black trees you have insert, delete, search, minimum, maximum, successor, predecessor, all take log n time, and it was asking basically how do you improve that? How do you give the first part said how do you modify the red-black tree data structure so that everything still takes log n time, except you speed up min and max to take order n, 1 time. Well, the first idea, the obvious idea, if you want something to get something in order 1 time, you keep a pointer to it. Okay? And so one idea is you sort of keep in your tree a special pointer from the root to the min and the root to the max. Okay? The trouble, and that's a good thing to do. The trouble is you have to make sure that that's still that's always a valid pointer. Okay, which means that you have to update it whenever you do an insertion or a deletion. Okay? If, let's say, you were to insert a new minimum here, then somehow that pointer's got to change. And so the important thing is that it asks which operation you have to modify. You have to modify insert and delete, okay, in order to maintain this thing, okay, and the correctness of it. Question?
You just make two separate pointers, not from root, but just...
Well, another possibility is you could keep them over to the side, okay? And they're not really part of the root, but they're sort of hanging outside the data structure. Then you would still have to modify these pointers. That every time you do an insertion, you have to modify these pointers wherever they're sort of stuck.
No, but, I mean, that's still all one operation.
No, it's not order. It's order 1 every time. No, it's not order 1. Okay? You've got to modify whenever the max or the min change. If you're always pointing to the max or the min, you've got to change the pointers every time the max or the min can possibly change. Which means that somewhere along the line, you've got to explain when you're going to change the pointers. If you do it whenever you do an insertion or a deletion, you're already spending or willing to spend log n time per insertion or deletion. If you do the potentially log n work, or depending upon how you do it, as long as you do that work, charge it at the same time you do the expensive operation, then it's always going to be accurate when you do a min or a max. Okay? It'll always take constant time then. Okay? But if not, you need to sort of know where, you need to be able to update those pointers. Okay? And while there are possibly different ways of doing it, you have to be clear when you're going to update those pointers and what you're going to charge for doing it. Okay? Any other questions? Okay? The second part of the problem asked to not only support not to support min and max, but to support predecessor and successor in constant time. Okay? And it should be clear that in order to do that, I mean, the easiest way to do that is to maintain at each node in the tree, to maintain a pointer to the predecessor and the successor. We've talked throughout this course about grandfather nodes and uncle nodes and brother nodes. In the interest of sort of being equal, we'll call these two pointers the pointer sisters. Okay? But anyway, for every node we'll have a pair of pointers. Okay? And for each, and what we've got to do again, if we're going to have a pointer to each one, we've got to make sure that we update it correctly. Okay? How do you update it? Well, whenever you do an insertion, okay, I'm now going to have to make sure that I stick this node is going to now have a pointer or a predecessor and a successor. It took me log time to insert this guy. In log time, I can figure out who its predecessor and successor would have been, and I can wire up the pointers correctly. Okay? Likewise, if I do a deletion, the predecessor node and the successor node have to be told that this guy is no longer around, and they be wired up to point to each other. So the purpose here is to show that for the whole idea of the data structure, you have these operations that are all balanced. Okay? And that you do the bookkeeping when you can do the bookkeeping. Okay? That's the underlying question here. Okay? Question?
And you didn't like the same structure for the question before?
Well, again, if you have a specific question about what you're doing, okay, we can talk about it some other time. Okay? But I mean, again, there's some questions. Some people may have tried to support a more general operation than just min and max for the whole tree, but min and max for a particular subtree, and maybe that involves more hairy schemes. Okay, that you have to involve. Okay, but if you're just going to try to figure out min and max for the entire tree, you don't need to keep pointers at every node. Okay, just one pointer for the tree. Okay, any questions about that? Okay. The second, the last question for the undergrads asked, consider the following algorithm for finding the maximum value in an unsorted array. Okay. So what was the algorithm? Basically, if the gap between the two things is, the two indices is 1 or less, then basically you take the maximum of these two elements. Okay? Otherwise, compute the maximum in the first half of the array, compute the maximum in the second half of the array, and return the maximum of those two halves. Okay? That's what the algorithm is doing. Okay?
So the first question was to explain why the algorithm was correct. Okay? And this was supposed to get you to try to think, well, what does the algorithm do? Okay, and why do you think it's correct, and why is it working? Well, the basic reason why it's working is, the maximum is either on the left side or the right side. Okay? And so you're going to compute the maximum of both sides. The maximum of each half is going to be the maximum of everything. So that's the basic idea for why the algorithm is correct. But the trickier part, okay, is what is the efficiency of this algorithm? How much time does it take? Okay? Well, to give you a hint, I said, well, write down a recurrence relation for this algorithm. How much time is it spending as a recurrence? The first thing to note is it's spending how much time per call in doing things. Well, in doing things, all that it's doing is it's computing the division of two numbers, and it's finding the maximum of two numbers. Depending upon how you want to do it, that's one operation or two operations. It's a constant number of operations. And what you're going to be doing is, to solve this problem on n numbers, you're going to do a constant amount of work, then solve the problem on half the numbers, and solve the problems on the other half. So the recurrence relation we get is t of n is going to be equal to 2tn over 2 plus O of 1. Okay? Because you're doing both halves. Okay? And a constant amount of work per split. Okay? Any questions about that? Okay? The second question asked, what was the running time of this algorithm? Okay? And there are a couple different ways you can think about this running time. I mean, the easiest way would be, now that you have a correct recurrence relation, solve the recurrence relation. And you plug it into the master theorem, and order n comes out. Okay? Some people, a lot of people, in fact, came out and said that this ran in log n time. And that you should have known was wrong, because it says that you're searching in an unsorted array. If you can really search in an unsorted array in log n time, talk to me after class. Okay? It can't be done. Okay? So that should have been, sort of as a sanity check, was not the right answer. A lot of other people came by and said that this was going to take n log n time. Okay? And that, as a sanity check, you should be a little suspicious if it's going to take you more time to compute the max than somehow linear time. That's not necessarily obvious, but that should have gotten you convinced that something was going on. Okay? The difference between this and quicksort is we're not spending linear time to partition. We're spending constant time to simply do that. Okay, any questions about that? Okay. Okay, the final problem, which was just for the grads, none of the undergraduates did attempt it, so I didn't have to take off any points for that, which was good. Okay, but for the for this problem, it said basically give a log n time to compute the square root of a number. Okay, and when you saw log n, you should immediately think binary search. Okay, what does binary search do? Well, basically, let's say we know that originally the square root has to be someplace between 1 and n. Of the square root of n has to be, bigger than greater than or equal to 1 and less than or equal to n. Okay, if it's a positive number. Okay, so for this one, let's find the middle point and square it. If the middle point squared is bigger than n, that means the square root has to be less than the middle point. So look on that side. Okay, if the square root is bigger than that, look on the if the square root on the other hand is smaller than n, the number squared is smaller than n, and that means that the square root is greater than or equal to it. So look on the other side. And basically, you're halving the number each time. Okay, so after log n iterations, you've narrowed the window down to the one number, which is the square root. Okay, any questions about that? Okay, there are a couple different variations of this that people did, but basically this is the idea. Okay, of all the variations, whether they look different or not. Any questions? Okay, so again, my feelings on this were that I mean, it was, there's a certain points where I could see people getting, let's say, running adrift. So I can understand, let's say, people missing one or two problems on this thing because they got lured away. But if you got, let's say, less than half, okay, it's at a point where you should be concerned about it, and we should come by and discuss it to see what you can do from there. Okay, any questions about the midterm or anything like that related to that? Okay, very good. Okay, now the
starting now, after the midterm, we're going to now start a different section of the course, okay, a little bit. The stuff that we talked about before were sort of preliminaries, basic sorting, basic data structures. And what I'd like to now start to talk about is the area called combinatorial search. Actually, this is going to be fairly brief. What I want to now look at is some more advanced algorithm techniques to speed up solutions to particular problems. Okay? We've really so far been limited to, like I said, to data structures or using sorting or things like that. And so for the next couple of weeks, I want to start looking at some more advanced techniques. We'll look at this. We'll look at dynamic programming. We'll look at graph algorithms. The other thing is that the next assignment you're going to be getting, okay, is going to be a programming assignment, okay, where the goal is going to be to try to come up with a fast algorithm, okay, and we'll talk about that towards the end of the class. Okay, so what's the idea when using combinatorial search? We've seen how when we use sorting, you can reduce, by using a clever algorithm, what seemed like an n-squared algorithm to n log n, okay? Now, the problems, the potential wins of a fast algorithm, that's a very substantial win, going from n squared to n log n. To give you an idea how substantial a win that is, I want you to respect that. If you think of a library with 5 million books, which a typical good college library will have, or a good university library may have 5 million books. If you think about their card catalog, okay, it would have had 5 million cards, maybe with subject cards, maybe 5 cards per book. You would have had 25 million cards to put in a card catalog. If it took you n squared time to sort that, there would never be a sorted catalog for books in the library. So going from n squared to n log n really made a big difference, okay, in terms of making jobs feasible. Now, the stakes become even higher when we look at problems whose time complexity is greater than n squared. Okay? What's the idea? For example, first day of class, we talked about the traveling salesman problem. What is the traveling salesman problem? It's a case where you've got a bunch of, there are lots of different ways you can phrase it. In the basic case, let's say we've got a set of points in the plane. We'd like to try to find the shortest tour that visits each one of these points, okay, and then returns home. So the idea for why you might care about this is as a machine tool wandering around. You have a robot arm. You want to put solder at all these points. How do you minimize the travel the robot arm has to make to connect the circuit board? And again, I've had companies come to me and need to solve these things. Okay, it comes up in transportation and robots, all kinds of stuff. Now, there is no known algorithm that runs in polynomial time for the traveling salesman problem. What do you mean by polynomial time? That means there is no n squared algorithm, or n cubed algorithm, or n to the 5th algorithm, or n to the 100th algorithm, or n to the 3000 algorithm known for this problem. Every algorithm for this problem takes time something like n factorial, maybe 2 to the n, grows exponentially. So if you want to try to solve one of these problems, these exponential functions grow extremely fast. The reasons why we liked logs were because logs grew very slowly. Well, logs were the inverse of the exponential functions. So exponentials grow unbelievably fast. So if you want to solve a problem like this exactly, okay, you're going to need to do something clever, okay, as far as searching through all possible solutions. Any questions? The reason why there is no known algorithm for in polynomial is because with a problem like this, it's inherent that you have to look at a large fraction of all possible solutions in trying to come up with the best one. Okay, so that's why we're sort of doomed to searching through it. Okay, any questions? Now, many of you will say, well, won't this problem go away if I use a supercomputer? Okay, that's people's natural tendency. Okay, and again, supercomputers will not help you solve this traveling salesman exactly any better than basically doing it by hand. Okay. When you move to a faster computer, it may get 6 times faster, 10 times faster. Actually, I was looking something up. Apparently, in the 13-year window, the clock speed of the fastest computer only went up by a factor of 6. So maybe waiting for the computer a few years from now, maybe it'll be 6 times faster. But if you have a problem that's really going to take time 2 to the n, if you have 6 times more computing power, since 2 to the 3 is going to be 8, if it's really going to take time 2 to the n, if you have a 6 times faster computer, that would mean that you could solve it for an n plus 3, where I could solve it in a problem of size n in the same amount of time. It's really not a significant difference, okay? So in an exponential machine, and maybe for a polynomial time problem, this might make a difference. But for an exponential time problem, you can't hope to win that way, okay? You might try to win by going to a parallel machine. Okay, a lot of people want to do that. They want to buy a machine with 1,000 processors, okay, or 10,000 processors. They think that's going to help them. But it won't. Because if you have 10,000 processors, what's the maximum amount of time you can get your job faster? If all the processors were doing something useful, which I doubt, okay, you've got 10,000 times faster if you have a 10,000 processor machine. Is that good? Well, it depends. I mean, you know, for some things maybe it's not bad. But if you're trying to solve a problem that runs in time 2 to the, let's say 2 to the n, okay, now you've got a machine that's going to run 10,000 times faster. You'll notice that 2 to the, what adds up to 10,000? I guess 2 to the, is it 12? 2 to the 12 or 13 is approximately equal to 10,000. Which means that this is going to be equal to 2 to the n minus 12. Okay, correct? 2 to the n is going to be equal to that.
Yeah,
Make it 13. Fine, it's 13. Tell you what, I'll be big. I'll make it 15. I'm not proud. The conclusion is the same thing. If you wanted to solve something, now if you give me a computer that's 10,000 times faster, you tell me you want to solve the traveling salesman problem on a printed circuit board with 100 connections. Now you're saying instead of it being 2 to the 100, it's 2 to the 85th. You still lose. You can't do that. Okay? It's making a very, very small impact, no matter how much you speed things up. Okay? So the basic idea is if you want to solve a combinatorial kind of a search problem, the only way to go is to try to be as clever as you can with your algorithms. By being clever with an algorithm, you can get a speed-ups of several orders of magnitude. Okay? And that's what I want to try to show you how to do over the next couple of this lecture, and I want you to discover how to do in the course of the next assignment. Okay. Let me give you an example of a problem I worked on once, where it was a combinatorial search problem, and we faced a similar problem and showed you what we did with it, to give you sort of an idea of how you can think about it. There was a problem that we were interested in. Okay, it's not an important problem. It's not going to be a very practical problem, perhaps. But there was a problem which had been open actually since 1849. The question was, if I give you 8 pieces in chess, you've got a king, a queen, 2 rooks, 2 bishops, and 2 knights. Is there a way to put them on a chessboard such that every square on the chessboard is threatened? Okay? Like, for example, here we've got these pieces down. If I pick this square, my claim is it's threatened by somebody. Who's it threatened by? The queen. If I pick this position, okay, who's it threatened by? The rook. Who's this one threatened by? Well, same rook. Let's try this one here. Who's this one threatened by? Bishop, okay. There's exactly 1 square on this chessboard that is not threatened by anybody. Can you figure out which one it is? Okay. It might be more obvious when you think about which one did I circle. This one. There is no piece threatening this square, this knight. Okay, which one is it? The rook? No, the rook's blocked. Okay, the rook, the queen can't get at it, the knight. 63 of the 64 squares are threatened. Okay? Well, this was discovered back in 1849, and they asked, is there a way to threaten all 64 squares simultaneously? Okay? Using just these pieces. Okay? And again, it's not an important problem, but if somebody's been thinking about a problem since 1849, they deserve an answer. Okay? So we started to think about how could you figure out if there is a configuration where every single square is threatened. Okay? Are there any questions about what the problem is? The problem here is we want to factor in blocking. Okay? You have to factor in blocking. Obviously, this rook could take that knight, except there's a bishop in the way. And we're using the standard rules of chess for this problem. Okay? So how would we go about trying to solve this problem? Okay? the immediate idea, since we're computer people, would obviously say, look, computers are fast. Why don't we write a program that simply tests every single configuration on a chessboard and see whether or not it's threatened? Okay, take every possible chessboard. Okay, count how many pieces are threatened. When we get to 64, stop. If we go through all possible configurations, we're done. You can't do it. Okay. Well, that is certainly a correct algorithm. But let's think about how much time that takes. You've got 64 squares on a chessboard. You've got 8 of them that you want to put pieces on. Because remember, the rules of the game, we were going to put the 8 non-pawn pieces on a chessboard. So how many ways are there to pick 8 pieces on a chessboard? Well, to put the king can go on any one of 64 squares. Okay? And then once you put the king down, the queen can go on any one of 63 squares. Okay? And then the first rook, well, can go on any of the other ones. Basically, you want to choose the 8 positions for your chess pieces. Okay? So basically, 64 choose 8 is the number of subsets of 8 positions to put on there. Okay? So when you do something like that, the number of possible boards turns out to be this ungodly number, which comes out to be about 10 to the 15th. Now, how many cycles per second does your computer do? Let's stop and think about it. You guys like to buy computers. You talk a lot about clock rates. How many cycles per second does your computer get? Does anybody know? 100 megahertz. Okay. What's 100 megahertz? Okay, in 10 to the something notation. Okay. 100 megahertz is 100 times, what's a megahertz? It's 10 to the 6th. So it's 10 to the 9, I think is right. Okay? So even on your super duper machine, okay, you get 10 to the 9th cycles per second. If you tested one cycle, now think about it. To test whether a board is threatened is going to take more than one cycle, certainly. Okay? It's going to take a lot of cycles. Okay? But even so, just think about the ratio. This is how many cycles per second you get. This is how many board positions you have to check. The ratio leaves you 10 to the 6th seconds if you can test each board in one cycle. In one cycle, you can execute a no-op, is what you can do in one cycle. Okay? So the answer is this is you can't do that in a reasonable amount of time. Okay? So what we really need to do is somehow reduce the space of possibilities that we look at. Okay? My bottom claim is that there's too many positions to look at if we just look at every single position. Okay? We've got to find a way to search all positions without looking at all positions. Okay? Which means we have to prune the search. Okay? Any ideas how we can prune the search? Get the effect of looking at all positions without actually looking at all positions. Okay? We could use symmetry of the board. Now, what's the point here? Okay? We're interested in which chess positions are non-threatening. Okay? We don't really want to, if you think about it, if a chessboard has a threatened position and we turn it around 90 degrees, it still has a threatened position. Taking the board and turning it 90 degrees has no impact on whether it's a threatening position. So what we could do is, okay, try to use symmetry to save this problem. So for example, suppose let's say we have a board here and we want to put down a queen. There's only going to be one queen, correct? Does it really matter if we put the queen on the left side or the right side? If the queen is the first piece we put down? No, because any solution where there was a queen on the left side, by taking a mirror symmetry of the board, taking all the pieces from this side and reflecting them to the other side, you're going to get an exact same solution. Okay? So the same number of squares will be threatened. So it certainly should be obvious that if we're just going to take the first piece on our board, which I say is the queen, It's not necessary to consider all 64 possible squares. Okay? We could limit the queen as its first position to lying on the left side. And in fact, even further, okay, question, yeah?
Yeah, but this only goes as far as the first piece.
This only goes as far as the first piece.
It loses its symmetry once the first piece is put.
That's right. Okay, but let's try to save something. Okay, the first piece, certainly the queen as the first piece could go either on the left or right. We might as well put it on the left. Likewise, the queen could also be either up or down. We might as well leave it up. Okay? And further, we could reflect the symmetry of our board going diagonal. Okay? So in fact, if we're only going to put down the first queen, it's possible, by just considering the queen as lying in this possible spots, if there is a solution, and we now try all possible combinations of all other pieces, we've solved our problem. If there is a solution with the queen here, there'll be a solution. If there is no solution with the queen here, and the other piece is free to move, there can't be another solution. So by doing this simple simplification, we've got from 64 possible positions down to 6, or down to 10, actually. Okay? So that saves a factor of 6 right off the bat. That's the difference between using a fast processor and a slow processor. Okay? Instantly. Okay? But it turns out there's better ways to exploit. Okay, how many people see what I mean by this? Okay, how many people do not see what I mean by this? Okay, so you want an explanation. Okay? What is the idea here? Let's try a simpler example. Let's say that we only have a 2x2 chessboard. Okay? And we want to figure out, is there a way to put, let's say, a king and a queen to threaten all squares? Okay? Well, if we put a king here, okay, and we find that there is no other way to do it. Okay, let's say it turns out, okay, if we put a king here, we will in fact threaten any other chessboard if we put a queen here, correct? Right? Okay, because the queen will threaten these squares and the king will threaten that squares. So in fact, with with a board like this, we could do it. But note that it's sufficient if we were doing this search. It'd be sufficient. We could also try to put the king here, or put the king here, or put the king here. My claim is it's not necessary. Because if we were testing all possible configurations where the king was here, if there was no way to do it, let's say we were going to try to do it with a king and a, I don't know, we'll call it a blank piece, which does nothing, okay? If we reflected the board position, stuck a mirror on the board here and reflected it, we would end up with our king here. Let's say it was a king and a queen, and the queen here, correct? If we reflected the board. If this was a threatening configuration, this will be a threatening configuration. Okay? So if we ask ourselves, if there is a threatening configuration here, we don't need to test the possibility of there being a king on this side. Because if there was a threatening configuration with the king on this side, by simply taking its mirror image, we would get a threatening position with the king on the left side. So without loss of generality, we don't need to test whether the king is on the left side. Okay? How many people are still confused by that? Okay? And again, once you believe that, the same idea holds. You can now reflect it down the other axis. Okay? And reflect it actually down the center diagonal axis. Okay? So the neat thing is by exploiting symmetry to see which situations were really duplicates, okay, we could save a lot of time. Okay? Question?
I understand all the symmetry except for the diagonal, but that's a slightly different kind of symmetry because you can be on the diagonal itself.
Oh, right. Okay, so what I'm saying is here I said 10 squares. Where does 10 come from? Okay? Actually, it's probably unlikely I'll be able to reconstruct it so fast, but let's see what happens. Correct? This is the upper quadrant of a chessboard. Okay? Which squares do you want? Including the diagonal, because you're right, we need to consider the diagonal.
How many squares are there that we're going to have to worry about? 4 plus 3 plus 2 plus 1, which is equal to 10. So you're right. We do have to factor in the diagonal, okay, because that isn't going to go away. But notice that any squares on this diagonal, okay, fall apart by the mirror symmetry. Okay? Namely, we could reflect the board over. If you put a king on this diagonal, by putting a mirror here, that's the same as putting the king here. Okay? So again, the key idea here is not so much this particular example, oh, you got to study chessboards. But the key idea here that's important is by using symmetry, we can reduce the amount of work we have to search. Okay? And by being clever about it, you can often do much better. Like, for example, this fact of limiting the queen to only 10 positions is not the most clever way to do this. What is the most clever way to do it turns out to be as follows. If we just limit the queen's configuration to lie in this quadrant of 16 and think of the white bishop as being restricted to one side of the board, it turns out that will enumerate all possible combinations. Because there's some symmetries about the relative positions of the queen and the bishop. Okay? And by factoring two of them in mind and convincing yourself of that, in fact, that this gives you a fewer number of configurations to test. Okay? You can reason about that yourself if you don't believe me. You should believe me about the 10 for the queen. Okay? And it should be clear that by factoring certain symmetries in with relative pieces, you might be able to do better. Okay? So anyway, when we did this, we found that we could now do it where we consider 16 possible positions for the queen, 16 possible positions for the white bishop, 32 for the black bishop, 64 for the king. You've got 2 rooks. The rooks are interchangeable. A white rook doesn't look any different than a black rook. Okay? So you pick pairs of squares for, you pick two possible pairs of positions for each rook, 2 possible pairs of positions for the knights. Multiply that together, we're now down to 10 to the 12th possible combinations. So by using symmetry, we knocked off a factor, in this case, okay, of 2 or 3 orders of magnitude, okay, just by using symmetry in a clever way. Okay? This is still too much to search in a bound. Okay? I usually find that when you're searching more than like 10 to the 8th positions, it gets to be quite time-consuming. So we still have to figure out a way to get rid of the number of positions, get that further down. But it should be clear that by using symmetry, we had a big win here. Okay? Any questions about that? Okay? Well, before we go back and try to speed up the job, we should make clear how do we go about testing all positions. Okay? Now I've told you that there's only a certain subset of positions on the chessboard I need to test. In order to make sure I test them systematically, I've got to go through them in a regular order. Okay? And the key idea to doing that is a technique called backtracking. Backtracking is simply a systematic way to go through all possible configurations of a search space. Okay? Depth-first search and graphs can, in some sense, be thought of as backtracking. Okay? Although here what we're going to be using it for is to go through all possible configurations of a search space. So how are we going to do this? What are we going to mean? Well, in our model of general backtracking, we're going to assume that our solution is a vector of possibilities. By a vector, I mean a one-dimensional array. Okay? And it's a list of ordered elements where each element is selected from a set. So what would be a vector solution for our queen's problem? Okay? We have an array. Okay? The first is going to tell us what is the position of the king. The second is going to tell us what the position of the queen is. Maybe rook 1, rook 2, knight 1, knight 2, bishop 1, bishop 2. Okay? Each square in here, if we have representing a number from 1 to 64, there's 64 possible squares on a chessboard. In every chess position, each piece is on a particular square, correct? So my claim is that we could represent any solution to the chess problem by a vector of length 8,
where each number in here is, each element is a number from 1 to 64. Okay? That's what I mean by this kind of a solution. Okay? It may seem kind of abstract here, but that's really what we're trying to get at. And what the idea of backtracking is, we're going to fill in this array of solutions, one element at a time, okay, in a systematic way such we make sure we miss no possibilities. Okay? So what's the basic backtracking algorithm? We're going to eventually want to build a vector of n elements, where n in this case happens to be 8. Okay? We're going to try to build from a partial solution. Okay? So suppose, let's say, I've already put down k elements. Okay? These are already now fixed. My goal is now I'm going to try all possibilities, okay, for the k plus first element. Okay? And as I add this element, I'm going to see whether or not it's still a legal possible candidate set. If it's not, then I'm going to backtrack. Okay? Meaning that there's no possible way of doing it, so I'm going to go and fix up something earlier in the permutation. Okay? And what backtracking is going to do is give me a nice regular procedure to do this. How does it work? First, I compute what are the set of possible positions for the first element. So what are the possible positions where the king can go as the first thing I'm putting down? Okay, what are they in the chess problem? Okay? All, okay, depending upon if I want to use symmetry, for example, I can list down the numbers 1 through 10. Okay? Because that's the initial thing I've used to remove symmetry. Very good. Okay? Now I'm going to say, okay, I'm now going to fill in the first position. So long as there's still a set of possible candidates to put in that first position, I'm going to pull one out, delete it from the set of remaining possibilities. I'm going to pull it out and use it, stick it into that first spot. I now, okay, have reduced the size of the number of elements in this set. I now check if the partial solution I put down by adding that element, if that really is a solution to my problem. If it's a solution to my problem, I print it out. Of course, by putting in the first piece, that's not going to by itself be a solution. Okay? If not, what I'm now going to say is, well, now I know what the first piece in my problem is. So let me now expand my counter to point to the second piece. And now compute the set of all possibilities for the second piece. Okay? That's what we're doing here. Suppose I put the first piece in the first position. Okay? What are the set of possibilities for the queen? Possible positions for the queen to go in as a second spot. Yeah.
2 to 64.
Okay, I don't want to put it in the first spot because I already have the queen occupying it. Okay? So why don't I put for the second one, it could be the numbers 2 through 64. Okay? And I now go through and come back here. Okay? Pick one of them. Okay? Is it a solution? No. If not, expand. And keep expanding until I've put down all my pieces. Okay? Until I have either come to a contradiction, okay, I've run out of elements, okay, in which case I can no longer advance, okay, or I find a solution. If not, what am I then going to do? Okay, after I no longer have a candidate to put into my spot, okay, I am going to back my counter up 1, which essentially deletes the last item, and then try the next candidate element from that set. Okay? And so the basic idea is I'm growing a partial solution. When I have trouble, I knock out the last element and replace it with the next candidate and try to grow it again. Then when I have trouble, back up, knock out the last element. And eventually either I'm going to grow to the end or I will eventually backtrack and run out of everything. Okay? And that is the idea of backtracking. Okay? Any questions about this? Okay? This I can see being a little confusing. There's a recursive formulation of this kind of algorithm, which may be easier to understand. Okay, if you like recursion, it should be easier to understand. What is the idea here? If I want to backtrack, okay, what I'm going to do is I'm going to start out, A is my partial solution so far. And K is sort of how many slots have I filled in that partial solution. Okay? If my partial solution is a solution, that's terrific. Print it out. If it's not a solution yet, well, why don't I now check out what happens if I expand it? Okay? Move K to K plus 1. Find the set of all possibilities for the next position. Then keep looping around. Insert one in. Okay? Take an element from the set. Stick that in and see what happens. Okay? One of two things can happen. After I stick the next element in the slot, maybe there's a way to complete it. If there's a way to complete it with that prefix solution, this backtrack call will find it. If not, it'll come back and say, I haven't found anything yet. Which means that the prefix that I gave it, namely this value of A to this call, wasn't enough. It wasn't the beginning of any solution. If so, what am I going to do? I'm going to stomp on the last element. Okay? And then go back, add another element, and call it again. And try to grow that. If after eventually I loop through all of these things, and I have never been able to extend it successfully, then I'm simply going to bomb out of this loop, which essentially decreases this by k. And it goes back to the previous recursive call. Okay? So my claim is that a recursive algorithm like this will iterate through all kinds of possibilities. Okay, are there questions about this? How many people think they sort of see it? How many people are sort of confused? Okay, a few people. Okay?
I have a question.
Yes, question.
What does it mean when backtrack and run out of the element?
Well, what does it mean when the backtrack runs out of elements?
Yeah,
Well, there's two different ways you can run out of elements. Let's think about this. One way you could run out of elements is that you increment k too many times. Okay? Which would be like, let's say you try to put a ninth piece on the chessboard. There is no ninth piece. Okay? In which case, the set of possible candidates is going to be empty. So that should bomb out at that point. Okay? The other case would be that you've tried all possibilities and nothing worked, in which case, your prefix so far isn't good, and you've got to correct it. Okay? Any other questions about this? Let me show you an example of really a fundamental backtracking application, which is constructing all subsets of a set. Okay? I mean, really, that what you're using backtracking for usually can be abstracted as being finding going through all subsets or going through all permutations. 99% of the time, that's really what you're doing when you're doing backtracking. What is a subset? Well, assume we've got n elements. We'd like to construct all possible subsets of n elements. What are all the possible subsets of 2 elements? Well, it could be 1 and 2. It could be 1, it could be 2, and it could be the empty set. Correct? Those are all the possible subsets you could make on 2 elements. What's the number of, all told, if you have n elements, you can make 2 to the n possible subsets. Okay? That's extrapolate from this, you can see that. So how do you construct all of these subsets? Well, the way that I would do it is to say, if it's 2 to the n, why are the number of subsets 2 to the n if you have n elements? My way of thinking of it is that you've got a position of you've got n possible elements. For each element, it's either going to be in or not in the particular subset. Correct? So we could model any subset by including a set of trues and falses. Okay? Where a true means that a true in the ith slot means that the ith element is there in the subset. A false in the ith spot means the ith element is not there. So what subset does this describe? True means 1 is in there, 2 is in there. This is a false, so 3 is not there. 4 is there, 5 isn't there. Okay? This set of trues and falses, this arrangement of trues and falses describes the subset 1, 2, 4. Okay? So this said, how do we construct all possible subsets? First of all, are there any questions about why this arrangement of trues and falses, how this trues and falses corresponds to a subset? Okay? How do you construct all possible subsets, given that this is true? Okay? Simple question.
What goes through all the binary combinations?
Construct all possible arrangements of true and false. Once you construct all possible arrangements of true and false, then you could, for every one of them, simply read the subset off like that. So how do you construct these things? We're going to go through our general backtracking algorithm. For each position, the items that could be in the kth position are either going to be true or false. Okay? We're going to report a solution whenever we've set all the k elements, all the elements, n elements, to be true or false. That's when we stop. Okay? If we just want to go through all subsets. So what happens if we use this algorithm to try to compute all possible subsets of 3? What are the set of possibilities for the first position? Let's think of our array here. What are the set of possibilities for the first position? What? What are the set of, okay, what in our vector here of solutions? We've got n elements. We now ask ourselves, what are the possible values for the first position? What? The two possibilities are, if you go through this idea, either true or false. Okay? Let's start off by putting a true there. That means that essentially we're putting the first element in the subset, correct? Now we go on to the second element. What are the possibilities for the second element? True or false? Let's start out by putting a true there. That puts the second element in. Now we move on to the third position. What is in the third position? Okay, what are the possibilities? True or false? We stick in a true. That's the equivalent of saying the third one is in. We now do our test. Have we inserted n items into the set? Yes. This has to be our first subset. Okay? Now we want to backtrack. We want to keep going. So we want to now change this value. This last value could have been a true or a false, right? Let's bop through that loop a little bit more. Now let's set it to be false. What does that correspond to as a subset? 1, 2, nothing. Okay? So now we've got 3 elements in our subset. Okay? They're 1, 2, and blank. Okay? This is our next subset. 1, 2. Okay? Any questions about what we're doing to here? Like, I don't understand is a good question. Yeah. Okay, you don't understand. Good question. Okay? What are we trying to do here? My claim is we have demonstrated that for every vector of trues and falses, this maps to a unique subset. Okay? By simply assigning 1, 2, 3, 4, 5 to each position, and simply writing down as our subset elements the ones that correspond to true. Okay? Do you believe that? Okay? So now my claim is iterating through all possible subsets is exactly the same thing as iterating through all possible trues and falses. So let's use backtracking to iterate through all possible trues and falses. There's n positions. Okay, so we're going to have a vector of size n. Each position is either going to be true or false. We want to go through them in the backtracking way. What is it that backtracking did? It kept considering all possibilities, inserting one, and then seeing what happened. When eventually it came down to a situation where there were no longer any possibilities, it backtracked. It subtracted 1 essentially from the position and tried to change that next position. So what happens when, what is the arrangement of things that we're going to do to our array as we go from 1 to 3. Originally, we set the first thing to be true. It's a choice of true or false. We stick true in it. Second thing has a choice of true or false. We stick in true. Third thing has a choice of true or false. We stick in true. Okay? Now, we're out of things to stick. We have filled up our array. This is a possible solution. Now we want to continue going. The last thing we inserted was this item. It's done its job. Let's now change it to the next item in the set. What was the other possible value for the last item in the set? Now we have true, true, false. Okay? This is also a solution. So let's print that out. That corresponds to 1, 2 as our subset. What is the next possible value for the third spot? There are no other ones. Okay? Which means if you say, give me more subsets of size 3 that start with 1 and 2, I've got to say there are none. Okay? So if you want more subsets, you'd better not start with 1 and 2, should you? So let's instead start with 1 and change this to be false. Okay? Change this to the second candidate that's possibly there. Once we now do that, now what's our possibilities? What are the possible values for the last position? True or false? Why don't we first try a true? What subset does that correspond to? What subset does that correspond to? 1, 3. Bingo. What's the next thing we do? We change the third item to false. What subset does that correspond to? Now do we change the what do we change the third item to? Can't do it. Okay? You're out of it. So this becomes a blank. What do we change the second item to? You can't change it to true because you already changed it to true. Okay? You cycle through the true possibilities and you cycle through the false possibilities. This is blank. What do you change the first item to? Okay? And now you start the process again. Okay? You put down a false here. What's the next possibility going to be? True or false? We might as well make it true. What's the next possibility? True or false? Might as well make it true. Bingo. What subset do we report? 2, 3. What's the next subset that we report? Okay. Next subset we report just has the 2 in it. What's the next thing we would do with this last position? Can't do it. What do we do with this next position? Change it to false. Now we've got false, false. True. Which subset is that? Sorry, okay. Which subset is that? Set this thing. What's the next subset we can do? What can we now change this position to? What can we change this position to? What can we change this position to? We've fallen off the end of the world. The program ends. Okay? So by doing this systematic search, okay, we've gone through all possibilities, okay, and we've pursued them in this order. Okay? Any questions about how you do this? Okay? This is kind of an important thing to be able to figure out how to do. Okay? So all subsets come from this. Okay? And again, once you understand the recursion, it's easy to see what it's doing.
Question.
Yes, question.
So if we went back to our chess example, then we really would have 8 possibilities for each of our...
Right. So how do we construct all... I'm going to answer your question with the next slide. What we really want to construct, do we want to construct all subsets of chess pieces in the, chess example? Not really. What we really want to construct are all possible orderings, okay, of positions. Okay, this is actually closer to permutations than subsets. What is a permutation? A permutation is an arrangement of the n elements. Here what we really want to construct for our example, remember, was all possible, in substance, the first 8 elements of a permutation. Yeah.
Yeah, but that's not my question.
Okay, what's your question?
I
Sorry.
just wanted to clarify the backtrack.
Right, okay.
If, for instance, we did, which we wouldn't
Right.
want to do because it would just be horrendous.
Right.
So in that case, we would have 64 positions each where we would cycle through 8.
Right, so what could we do if we wanted to do the chessboard example? The first position could be anywhere from 1 to either 64 or 10, depending upon what you wanted. Then, if you use symmetry, it would have been down to 10. Then you considered all possible king positions, rook positions. And we're slowly putting down one piece on the board saying, is this okay so far? Is this okay so far? Is this okay so far? Oops, it's not okay. Let me try the next possibility. Oops, it's not okay. Backtrack. Try the next one. Try the next one. Oops, it's not okay. Backtrack. Same thing as before. Okay? How do you construct all permutations instead of subsets? Well, permutation, remember, was an arrangement of things. How many permutations are there of 3 items? Okay, 3 factorial, which is 6. What are they? They're 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 2, 2, 3, 1, 3, 1, 2, 3, 2, 1. Correct? How do we go about doing it systematically? The way I would do it is, how many cells do you want to create in your vector? How many positions are there that you want to fill? 3. In general, if you have an permutation of n items, n cells. What are the possible candidates for the first position? Any number from 1 to n. Once you put down a number here, what are the possible candidates for the second position? N minus 1 candidates, which are they? Any number except the guy that's up front. Okay? What are the candidates for the third position? Which ones are they? Any item not included so far. Okay? So by systematically using this as our subset and backtracking, we can iterate through all possibilities the exact same way we iterate through all possibilities of subsets. Okay? Any questions about that? Okay? Very good. Now, how would we save over on our chessboard example? What were we going to do with our chessboard example? Okay? Well, in our chessboard example, we wanted to try all possible subsets of 8 positions, okay? Or equivalently, all possible first 8 elements of a permutation, basically. What we would really like to be able to do is to prune our search. What does pruning search mean? It would be nice if we reached a contradiction where we know before we have filled in the entire array, it would be nice if after filling in this many elements of the array, we could show that there was no possible way to finish the job up. Why? Because if after showing I put queen, king, 3, 4, if I could show that if once you've put these positions, if at this point I could decide, look, there's no possible way to finish the job if you started this way, I don't have to go through all the possible orderings that would follow from filling this thing. If I could make a decision that after you've put down a few pieces, you've done something bad, I could backtrack immediately without going through all possibilities. That is what we mean by pruning. Okay? So how, in our chessboard example, might we be able to prune search? Okay, question, or idea.
Yeah, well, we could take the pieces which only threaten a few other positions last and have a counter how many spots on the board are not threatened yet.
Okay, good idea. Okay, what's the idea? Suppose we have taken every piece and figured out what's the maximum number of squares that have been threatened. Okay, what's the maximum number of squares a queen can threaten? Well, a queen can threaten along a row or a diagonal, or a row or a column or a diagonal or a diagonal. Any queen can threaten at most 28 squares, 27 squares. A king can threaten at most 8 squares. Why is that? Well, I mean, it only threatens the guys around it. There's 8 squares that it can threaten. Suppose we have put down 7 possible pieces already. There are 9 squares that are unthreatened so far. And all I have left to do is to put down the king. Is there any place I can put that king to cover all the squares? No. The square can, the king's sort of a weak guy. He can only threaten 8 squares. You're telling me I have 9 squares for you to guard, and I can only guard 8. Does it bother me to put me in all possible positions to say, well, can I guard him from here? Can I guard him from there? Can I guard him from there? No. The instant I know that the number of unthreatened squares exceeds the maximum amount of firepower I have sitting on the sidelines, I know that the way you put your pieces now is hopeless. Can't help you get to where you want to go. Okay? And this means I can now prune my search based on my predecessor. Okay? How many people sort of see what's going on? How many people are confused by that? Okay? The neat thing is that by doing this thing, I can prune my search and eliminate a lot of possibilities. Okay? How much could this help? Well, when we were doing this project, we implemented a backtracking search where we pruned based on how many different, How many different, on this power threatening, this coverage threatening scheme. And when we did that, we found we eliminated 95% of the search space, which meant that we eliminated 19 out of 20 positions we had to check. Okay? That saved our time by another factor of 20. Okay? But in the program we were working on, saving another factor of 20 over 10 to the 12th wasn't good enough. Okay? It still would have taken over 1,000 days to run. And so by using them, we had to go back and think of a much more clever pruning scheme. And ultimately, we're able to get it down to the point where we could solve it in less than a day. Okay? The more clever pruning scheme is kind of complicated. I don't want to go into it now. But the moral here is, if you take your basic search problem and do a clever pruning, you can get a lot more work done than if you do it in a naive way. And to prove it to you, I give you the next homework assignment. Okay? I just want to introduce it now, and we'll talk about it next class a little bit more. What is your problem going to be? You're going to write a program to solve the backtracking, the bandwidth problem. What is the bandwidth problem? Suppose I give you a graph, okay? A graph being a set of vertices and edges. You want to lay down the vertices in order such that no edge spans a lot of distance. Okay? Suppose we had a graph here where vertex 1 was connected to vertex 8, connected to vertex 10, ... It's clear that you've got here, if your graph was just a simple path, by laying it out in this way, first vertex, second vertex, third vertex, fourth vertex, you get a lot of very long edges. Correct? But if you laid it out as a path where adjacent vertices were, no edge is ever longer than 1. Okay? Now, in general, there are a lot of reasons why you would want to lay out a graph such that the bandwidth is low. By the bandwidth, mean the length of the longest edge. Okay? For example, it comes up in linear algebra. If you can take your matrix and make it into a banded matrix, you can do certain operations much faster. It comes up in circuit layout. Okay, you want to minimize wire lengths. It comes up in using memory, in trying to optimize memory usage in certain hypertext systems. Okay? So minimizing bandwidth is something you'd like to be able to do. Okay? And it's something you're going to want to do for your project, for your assignment. I urge you to, the assignment sheets are in the back of the room. Take a look at them. We'll talk more about it, the assignment next class. But I want you to start thinking about it. Okay, thanks for your attention. See you then.